Hello, this is Sabir. Uh, so in this lecture, I'm going to discuss all about the uh, global patterns of tectonic stress. That means what kind of stress or in which part of this world, what kind of stress are acting, right? So today's discussion is all about the global patterns of tectonic stress. It's about this global global pattern of tectonic global pattern of tectonic stress. So in this lecture, basically we will concentrate. So what kind of faults are responsible for what stress, due to what stress, and in the stress orientation along the global state, because and which portion of this art, which stress are dominantly active or dominantly non-active, so that we can analyze so what is going on over there and what are the responsible things or something like that, right? Okay. So before I go, there are a lot of techniques to measure the. You have already known that what are the techniques. So there are a lot of techniques to measure the global pattern of tectonic stress. So one of this is earthquake focal mechanism. Earthquake focal mechanism, or GPS, or geodetic studies. GPS or geodetic studies. So from there we can also find out the tectonic stress of global pattern of from in the large scale, something like that. In geological in situ or in situ measurement, right? We can go to the field and we can go to the field and we can measure the in situ stress of that. And there are a lot of stress, like oil bore or something like this, borehole. From the borehole, even we can identify the stress of stress. Yeah, so there are a lot of techniques. There are a lot of techniques from where we can identify the global pattern of tectonic stress, or any regional or any local stress, something like that. But early attempts to find out this are very limited, and especially earthquake focal mechanisms were used in early stage before the advent of GPS or geodetic or other in situ measurement techniques, something like that. Initially this was attempted in United States. So Joback and Joback and Joback in 1980 categorized the patterns of global states in the following way. So I'm going to show you here. Okay, this should be great. Yeah, here I'm going to larger the size so that you can understand. Yeah. So here, if you see here, the initial effort to apply this integrated mapping strategy, I'm going to integrate it. Integrated mapping strategy means here I meant here integrated mapping strategy means applying all the procedures here in integrated apply mapping strategy, applying the earthquake focal mechanism, earthquake focal, all the techniques we have available, right? Or GPS or in situ or something strategy to the to the inner stress reveals two fundamental characteristics of crustal stress field. Two fundamental crustal stress field. Number one here, the first order, the stress field is uniform with depth throughout the upper brittle crust, as indicated by the consistency of stress orientation inferred from the different data types sampled different volume. That means, what does this mean? This just means that stress we measured, or stress is measured with depth, are uniform throughout the upper brittle crust. So we know if this is the brittle crust, then the mantle, something like that. If this is the mantle and this is the crust, then this is the upper brittle crust, and the stress field is uniform here throughout the depth, throughout its depth, right? Is uniform upper brittle crust as indicated by the upper. So this stress orientation or the uniformation or something like that is consistent with the stress orientation inferred from different data that sample different volumes of rock at different depths. So what the data measured from the in situ or geologic stress measurements are consistent with this statement. And the arcade focal mechanism, which provides the spatial resolution, which provides the covers depth between 5 to 20 kilometer. So an oil bore breakout and drilling induced fracture data commonly sample 1 to 4 kilometer depth in some cases, as deep as 5 km, providing the valuable link between the near surface and the focal mechanism data. So the stress you have got from here 1, 2, and 3 are consistent with the stress field that we say uniform with depth throughout the upper brittle crust, and that was found by the Jobak and Jobak in 1980. Okay, so stress orientations are remarkably uniform over broad regions. So what is the stress orientation? The orientation of stress. So we know already the principal stress, sigma 1, sigma 2, and sigma 3. So the orientations of this stress field, that means orientation of sigma 1, sigma, and sigma 3, are remarkably uniform over broad region, length scales up to thousands of kilometers. So we'll see later on about that. So despite large changes in crustal geology, tectonic history, and crustal thickness. So despite of these three conditions, number one, crustal thickness, two, tectonic history, and three, crustal geology, stress orientations are remarkably uniform over broad region. It can be up to thousands of kilometers. Okay, so there's two broad conclusions about the crustal stress field were made by Jobak and Jobak 1980 and 80. Okay, so now we will discuss all about the stress regime. Stress regime. So what is stress regime? Similar to stress orientation, so we have already seen what is the stress orientation, right? So similar to stress orientation, stress regimes also shows a marked regional uniformity. So what is stress regime? Stress regime is nothing but the what kind of stress or kind of stress orientations are located in different parts of the world, different parts of the plate boundaries or something like that. So before we going to start or before going to discuss all about the stress regime, we have to understand different fault types and the different fault types and responsible stresses for that kinds of fault, something like that. So before I go, so we have already discussed in the stress classes that principal stresses, right? So we have already know the principal stresses where there are no any shear stresses, and this there are three principal stresses, right? Principal. So you have already know what are the principal stresses. There are three principal stresses: sigma 1, sigma 2, and sigma 3. So sigma 3 is the minimum principal stress. This is the minimum principal stress, and sigma 1 is the maximum principal stress. Maximum principal stress, and sigma 2 is the intermediate principal stress. Intermediate principal stress, and the tensor of principal stress is nothing but sigma 1 0, as all other shear forces are 0 0, sigma 2 0 0 0, and sigma 3. These are the principal stress tensor. So we have three principal stress, right? So the orientations, different orientation of sigma 1 and sigma 2 results different kinds of fault. So for example here, so we know from the there are three types of faults available here: normal fault, two reverse fault, and three stack slip fault. Stack slip fault. So now I'm going to discuss which forces or what is the orientation of principal stress in case of normal fault and in case of reverse fault and in case of stack slip fault. Oh, I'm sorry, my laptop charge is going to finish, so I have to start that. Hi, welcome back. So I came. Yeah, welcome back. I'm sorry because my laptop charge is going to finish right now. Okay, so different stress orientation results different kinds of fault. So normal fault. So in case of normal fault, say for example here we have a block here. We have a say apple. Oops, I'm sorry, my laptop charging is making this stuff for me. Okay. I hope it works right now. Yeah. So for example, here is the upper brittle crust or something like that. So there is a block or something like that. So if we compress it, or if there is if stress orientation, in case of stress orientation, if the maximum principal stress is the tensile stress along the uh, here say the least or minimum principal stress or tensile, something like that here, and the maximum shear maximum principal stress is the vertical, say here, then we'll find this is the maximum. So if there is a blow, then the minimum principal stress are tensile here. That means a force will go here and force will go there, that means it's tensile, and the maximum principal stress is vertical. So it will go after, if this kind of force orientation are here, then the block will be subjected to something like that. And there are some faults developed here, because right, so these faults are called normal fault. FAULT, normal fault, right? So for normal fault, minimum principal stress is horizontal here, and the maximum principal stress is vertical. And in this case, maximum principal stress is nothing but the gravitational force. Gravitational force, right? So in case of reverse, so we can make a conclusion that normal faults occur especially in the tensile regime, or where there is a tensional forces are actively occur in these regions. Are normal. We may expect the normal fault or something like that, right? Yeah. So reverse fault. So consider same way. There is a block here. There is a block here, and in case of reverse fault, if we apply the maximum shear stress along the maximum horizontal, and there is a minimum say sigma 3 is minimum principal stress, minimum sigma 3 is principal vertical, then the reverse fault occur, and it will shorten because sigma 1 is greater than sigma 3. So definitely this block will be shortened, and the block will be something like that. There is a fault here, right here. So this kind of fault developed here is called the reverse fault. This kind of fault is reverse fault. So for reverse fault, we may conclude that reverse fault generally occurs in a compressive region, where minimum principal stress is vertical and the maximum principal stress is horizontal, and intermediate principal stress is horizontal as well. Here the maximum principal stress, intermediate principal stress horizontal as well. So in normal fault, sigma 1 is vertical and sigma 2 and sigma 3 is horizontal, right? Here for the reverse fault, sigma 1 and sigma 2 is horizontal and sigma 3 is vertical. Sigma 3 is vertical. So so when reverse fault occur and when normal fault occur, and that is one of the another fault type. Stack slip fault is here. So for example, here we have a block separately something. Sorry, a large block here, right? So if we apply forces this way and this way, then it will be something like that. If this is a sigma 1, if this is sigma 3, then the block will be something like that. Sigma 1, so that means this block will displace more rather than this. So this one, right? So this one is the sigma 1 and this one is sigma 3 and the vertical force is sigma 2. Vertical force is sigma 2. So in this kind of fault is this way and this that way, right? Yeah, this kind of fault is called stack slip fault. So it's stack slip fault. In case of stack slip fault, sigma 1 and sigma 2 is horizontal and sigma 1 and sigma 3 is horizontal and sigma 2 is vertical, right? So so what kind of orientations may result different kinds of fault, right? So different orientation of this principal stress may result different kinds of faults here. You see. So now we would like to see, or we'd like to see the global pattern of stress, or where in which plate tectonic boundaries, which kind of orientation are responsible for that. So let's go to the fall where you can see. So this is the global stress map, global horizontal stress map. So from the stress map, there is a different color here, so right? So red color is normal fault, green color is strike slip fault, and blue color is reverse fault. So from there we see there are a lot of normal faults occurring along this boundary. So these are the South American plate, and this is another plate. So this plate boundary, there is normal fault occurring. So and there is also normal fault occurring here. Normal fault occurring maximum, the normal fault. So not in this region. So we may conclude that in this region, the two blocks are separating. Two blocks are separating, right? Two plates are separating because the tensile forces are working over there. Here two blocks are separating, so I think this block goes this way and this block goes that way, or something like that. That is should be right. Yeah, so normal fault is locating in that region where there is tensile force are actively working. Okay, so green forces are strictly false. So we see there are some green forces here, strictly force, especially in Himalayan region here, and here we see San Andreas Fault is located here. San Andreas Fault is one of the greatest example, or one of the good examples for strictly faults are still active here. So at the green, so we can conclude that here the green strictly force or something. We know the text lead for sigma 1 and sigma 3 is horizontal, so that means horizontal pressure, horizontal stress are mainly predominant here in this region and in this region, and here at the southern part or of the Alaska as well. So it's text lead fault. Blue, we see there are some blue regions here as well. So there are some blue is for reverse faulting. So blue, uh, so we know the compressive regions are responsible for compressive regions are reverse faulting. So we know that here sigma 1, that means the maximum principal stress is horizontal here, and the least principal stress, that's the minimum principal stress, is uh, vertical here. So we see the global patterns of tectonic stress, and that is very complicated because we see there are some regions where horizontal force, the same time vertical force, actively working, and and in some other regions both and even three types of faulting are three types of fault, especially here in Himalayan region. Three types of faulting are here predominant: red normal faulting, green spectral faulting, and blue here the reverse faulting. So global pattern of tectonic stress is complicated, right? Yeah. So there are a lot of research that are ongoing to resolve this kinds of problem and to understand the procedure, something like that. So I hope you have understood or you have enjoyed this lecture. I'm sorry for my English language problem because my English is not so good to make you understand, but I'm trying to make you understand uh, as I can. Thank you very much for being with us, and do not forget to subscribe me. Thank you.